In section 2, we defined the condition for equilibrium, rotational and translational equilibrium. But in section 3, we are going to study the conditions or the cases which the object is in not rotational motion. Now let's remember, if sum of the torque acting on the object is equal to 0, so then there is an equilibrium. In this case, angular acceleration of the object is equal to 0. However, if sum of the torque is not equal to 0, what's going to happen? So assume that you are applying a force on a disc and you are rotating it with your hand. What's going to happen? It will accelerate. So there will be an acceleration. So then, if there's an acceleration between the torque and acceleration, so if you increase the torque, acceleration must increase. And between this torque and acceleration, there must be a relation. This relation can be written by this equation. Sum of the torque acting on the object is equal to I times alpha. So what is I? I is known as moment of inertia. Moment of inertia. What is it? What is moment of inertia? In fact, it is very similar to translational motion. Remember, if sum of the force acting on the object is equal to 0, so we said that acceleration of the object is 0. Object is not speeding up, slowing down. But if sum of the force acting on the object is not equal to 0, in this case there will be an acceleration. And we wrote this relation between these two quantity. Sum of the force acting on the object is equal to 0, mass times acceleration. So mass is in fact known as inertia, but it is or mass is a measurement of inertia. These two equations are very similar. Sum of the force acting on the object is equal to mass times acceleration, linear acceleration. Sum of the torque acting on the object is equal to I times angular acceleration, which means moment of inertia is rotational analog of mass. In translational motion, if mass is big, you cannot easily accelerate an object, or you cannot easily slow down an object. In rotational motion, if moment of inertia is big, you cannot easily accelerate an object in rotation, or you cannot easily stop the rotation. So moment of inertia and mass are similar thing. One of them is in translational motion, the other one is in rotational motion. Now let's get back to the text. So the following water exerts a force on the rim of wheel, producing a torque that causes the wheel to rotate. Yes, if water applies a force here, it produces a torque there and causes an acceleration, angular acceleration. So other forces such as air resistance and the friction between the axle and the wheel produce counteracting torque. Of course, this falling water produces a torque, but other friction force or air resistance produces a counteracting torque. If these two are equal, which means sum of the torque acting on the object is equal to 0, so then this is the condition for rotational equilibrium. So then this wheel will rotate with constant angular speed. When the net torque on the wheel is not 0, so if the water is applying a greater torque, so then the wheel's angular speed changes. Yani an angular acceleration alpha appears. So a net positive torque causes a positive angular acceleration, a net negative torque causes a negative angular acceleration. It's very simple because the relation between them is this. Sum of the torque acting on the object is equal to I times alpha. If this is positive because this is a scalar quantity. If this is negative, this is negative. So in translational motion, remember, if a net force applied on the object gains linear acceleration. Second law of motion, this is known. And sum of the force acting on the object is 0. If a net torque is produced on a object or in a rotating and object gains angular acceleration, object starts spinning faster and faster. This is known as second law of Newton's second law for rotation. Because these two equations are very similar. Sum of the force acting on the object is equal to mass times linear acceleration. Sum of the torque acting on the object is equal to moment of inertia multiplied by angular acceleration. So moment of inertia is a measure of object's resistance to change in its rotational motion about some axis. Yeah, if the object is rotating, it does not want to stop. If it is at rest, it does not want to rotate. So it is definition is, as you see, very similar to inertia of translational motion. However, moment inertia is, as I said, moment inertia is the rotation analog of mass. What does it mean? In translational motion, there is mass. In rotational motion, there is moment inertia. They have the same function. Moment inertia has a unit of kilogram meter square. Why is it like this? We are going to explain. The inertia resists change in translational motion. Yes. The moment inertia resists change in rotational motion. Yes. Mass is an intrinsic natural property of an object. Mass is measurement of inertia, remember. But moment inertia of an object depends on object's mass. Yes, mass exists, but also the distribution of the mass around the axis of rotation. What does it mean? For example, you can rotate this pen from midpoint very easily. Or take a beam and then you can rotate it from midpoint. But if you hold it this way, it becomes a little harder to rotate. So then, because it's the same object, so its mass is the same. In this case, we didn't change the mass. However, we changed the axis of rotation. When we change the axis of rotation, it becomes harder or easier. As you see, moment inertia depends on object's mass, is heavy or not. Also depends on where about which point object is rotating. So about this point harder, about this point easier. So the farther the mass of the object from axis of rotation, the more difficult it is to rotate the object, the greater is the object's moment of inertia. So moment inertia of different shapes can be calculated by mathematically. For example, this is a point mass about an axis. What does point mass about an axis mean? For example, Earth is revolving around the sun. It's a point mass. Or a bob connected to a string is revolving on a circle. It's a point mass. So point mass about an axis, if it is moving, so its moment inertia is mr squared. M is the mass of the bob or object. R is the radius of the circle. A tin hoop, it's a circular-shaped object. A tin hoop, it's a loop. About symmetry axis, this is called symmetry axis, the axis passing from the center. So it's a hoop or a ring. If it is rotating about this axis, its moment inertia is the same as this, mr squared. Mass of the ring multiplied by square of the radius. But if you rotate this tin hoop about diameter, not symmetry axis, about this, so in this case, moment inertia decreases. So it is easier to rotate about the diameter a ring. So 1/2 mr squared is the moment inertia. For a disc or cylinder, moment inertia about the symmetry axis, which is the axis passing from the center, is 1/2 mr squared. It's similar, equal to these two. Solid sphere about diameter. Its moment inertia is 2/5 mr squared. M is the mass of the sphere, and R is the radius of the sphere. Spherical shell, which is a basketball, and inside is empty. About diameter, its moment inertia is 2/3 mr squared. A thin rod about the perpendicular axis to the center. Moment inertia 1/12 ml squared. L is the length. Thin rod about the perpendicular axis to the one end. So moment inertia 1/3 ml squared. So as you see, this is harder to rotate. Remember, we said this is easier, that is harder. How many times easier and harder? 4 times. Okay, so these are the equations for a few shapes. Normally in the exams, these are given. These until now they give, but better to learn them in the case of the question. These equations are not given. Okay, so sample problem. To see, it says a student tosses a dart using only rotation of her forearm to accelerate the dart. So you throw the dart this way, like this. So the forearm and dart have a combined moment inertia of 0.075 kilogram meter squared. So moment inertia is 0.075 kilogram meter per squared. About the axis, elbow is the axis right here. And the length of the forearm from here to there, it is equal to 0.26 meter, which is the radius of the circle drawn by the dart, which is 0.26 meter. If the dart has a tangential acceleration is 45 meter per second squared, tangential acceleration is given here. So what is the net torque on the arm and the dart? We will find the torque. So, however, in your equation, in torque equation, net torque is equal to I times alpha. Alpha must be known. alpha must be calculated. But tangential acceleration is given. But we know from the chapter 1, tangential acceleration is equal to radius times angular acceleration. We can calculate angular acceleration. Tangential acceleration 45, radius 0.26. Alpha, we will find alpha. So alpha is 173.1 radian per second. So now calculate the torque. I is given combined I 0.075. Angular acceleration you calculated. Multiply these two, you will find torque produced by the 4R. mr squared is. Okay, next one is the angular momentum. Because the rotating object has an inertia, it also possesses momentum as associated with its rotation. This is called angular momentum. Remember, in 11th grade you studied if an object is moving with a speedy velocity, this object is a linear momentum. So, and we can calculate the linear momentum of this object by mass of the object multiplied by velocity of the object, which is the linear momentum of the object. In rotational motion, object is not moving with a speed, it's rotating with an angular speed of omega. Object has it has not a rotational analog of mass's moment inertia. If you multiply moment inertia with the angular speed, you will calculate the angular momentum of this object. So angular momentum is a unit of kilogram times meter squared times kilogram times meter squared times 1 over second, because radian per second is 1 over second. Radian is not a unit, remember, it's not a dimension, you know. Kilogram meters per second is the unit of angular momentum. So this is the angular momentum. Now let's solve a question about angular momentum, how to calculate it. Last year they choose some information from the sample problem and then make a ministry exam question. So it was like this. A 525 kilogram merry-go-round whose radius is 2 meters is rotating with an angular speed of 0.2 radian per second. Calculate its angular momentum. So L is equal to I times omega. I is for merry-go-round, it's a disk. 1 over 2 mass of merry-go-round times square of radius of the merry-go-round multiplied by angular speed of merry-go-round. So omega. So now 1 over 2 mass of merry-go-round 525. Radius of merry-go-round 2 square of 2 multiplied by angular speed is 0.2. So when you multiply these numbers, you are going to get the answer. 525 times square of 2 is 4 times 0.2, so 0.2 divided by 2, it is 210 kilogram meter second square divided by second. So this question is, this sample problem is asked last year as a ministry exam question in this form. So mass is given, radius of the merry-go-round is the angular speed is given, calculate the angular momentum of merry-go-round. Okay, the next one we are going to show is the conservation of angular momentum. What does conservation and angular momentum mean? If something is conserved, it means it's constant. It is very similar to conservation of the linear momentum. In translational motion, linear momentum is conserved. In rotational motion, angular momentum is conserved, which means if net force acting on the object is 0, linear momentum is conserved, which means last year you studied m1 v1 is equal to m2 v2. Linear momentum does not change total volume. If mass decreases, speed increases. If speed decreases, mass increases, or vice versa. In rotational motion, if the net torque acting on object is 0, this is condition. Net torque acting on object must be equal to 0. Angular momentum is conserved, which means initial moment inertia times initial angular speed is equal to final moment inertia times final angular speed. What does this mean? For example, this spinning ice skating woman, if when they start to spin around its axis, when it decreases the moment inertia of her body, so if moment inertia decreases, she starts to spin faster because total angular momentum of the body is conserved. So if the moment inertia of such a system decreases, if the moment inertia of such a system decreases by time, its angular speed increases. Once again, let me repeat. If the moment inertia decreases, angular speed of the system increases. Okay, let's solve a problem. It says a 65 kilogram student spinning on a merry-go-round that has a mass of 525 kilogram and a radius of 2 meters. If the angular speed initially is 0.2 meter, what is the angular speed when the student reaches a point 0.5 meter from the center? So student initially at the rim, somewhere here. So there are two components in this system. One of them is the merry-go-round, second one is the student. So the student is at a radius distance from the center of axis of rotation as 2 meters, which is the radius of the merry-go-round. But later, student starts to walk and approaches to the center, somewhere here. So this final distance is 0.5 meters. So now when the mass distribution comes closer to the axis of rotation, moment of inertia decreases. If moment of inertia decreases, so according to conservation of angular momentum, definition of angular momentum, if moment of inertia decreases, to keep the angular momentum constant, so angular speed must increase. Yes, final angular speed will be greater than initial. Initial angular speed is given here as 0.2 radian per second. We can predict final angular speed will be greater than 0.2 radian per second. But how much? So, as I said, system have two components. One of them is the merry-go-round itself, so its moment inertia does not change. So merry-go-round, Im is equal to, so it's a disk 1/2 m r squared, here and there, the same, 1/2 m r squared. Let's calculate this. 1/2, mass is 525, r is 2, square of 2, so it is almost 1050 kilogram meter squared. So right here also I am 1050 in the second case because shape of the merry-go-round does not change. However, right here student is at a distance of 2 meters. So student has initial moment inertia. Student is moving in a circle because the merry-go-round is rotating. Student is moving in a circle. It's a point mass. If a point mass is moving in a circle, its moment inertia is mr squared. Mr squared. M is for student is 65. R is initially 2, square of 2. So we are going to multiply 4 by 25, 4 and 65. 65 multiplied by 4, it's equal to 260 kilogram meter per second. But right here in the final cases, student is not now at 2 meter away. It's 0.5 meter away. So its moment inertia has changed. Our final square is initial. Mass is 65. Final is 0.5, square of 0.5. Now let me do this. 0.5 square, 0.25 multiplied by 65. It's equal to 16.25. Now, because system, I'm talking about the system, so because whole system is rotating with this initial angular speed, I'm going to find initial angular momentum by adding them. 150 plus 260 initial one. So 150 plus 260, which is equal to 1,310 kilogram meter square is initial moment inertia of the system. Final moment inertia, let's find it, 1,050 plus 16.25. Now, 1,050 plus 16.25. It's almost equal to 1,666 kilogram meter square. Now we apply the conservation angular momentum. So initial moment inertia times initial angular speed must be equal final moment inertia times final angular speed. So initial angular speed is initial moment inertia 1,310. Initial angular speed 0.2. So final moment inertia 1,066 times final angular speed. Now divide this 1066 and you will find what final angular speed is. 1320 multiplied by 0.2 divided by 1066. So answer becomes 0.024. So 0.24, sorry. Omega final becomes 0.24 radian per second. So this is the answer of the question. The last title is the rotational kinetic energy. Remember, in translational motion, if an object of mass is treated as a point mass, translational kinetic energy is 1/2 mv squared. But if an object is rotating, in this case, instead of m, we are going to write I. Instead of v, we are going to write omega. So then 1/2 I omega squared is rotational kinetic energy for an object if the object is rotating about a specific axis of rotation. So this is the kinetic energy, translational kinetic energy. This is about the rotational kinetic energy. Anyway, so, but sometimes, yes, object can rotate and spin about an axis, its own axis. For example, here is falling basketball. Falling basketball has, if it is falling, it's translational motion, so it has a translational kinetic energy 1/2 mv squared. But if basketball is spinning about one axis of rotation, it has a rotational kinetic energy 1/2 I omega squared. However, if basketball is rolling, in this case, it has both translational and rotational kinetic energy. You should add these two to find the kinetic energy, total kinetic energy of the basketball. In this case, now let's apply this. If the force of gravity is the only external force acting on the object, mechanical energy, which means sum of the potential and kinetic energy associated with the object, is conserved. Now what does it mean? Remember, in the language you learned them, if this pen right here, it is a potential energy, but if I release it, it falls down and hits the ground with a speed, because potential energy of this pen converts to kinetic energy. It is similar. When you put a sphere at the top of the inclined plane right there in the altitude h, it has a potential energy. Because it's at rest, it has no kinetic energy. But later, it starts to roll. And at the bottom, its potential energy right there completely converts to rotational kinetic energy. So rotational kinetic energy right here, it's translating with speed v, also rotating with angular speed omega. So it has total kinetic energy 1/2 mv squared plus 1/2 I omega squared. According to conservation of mechanical energy, at the top of the inclined plane, potential energy, which is mgh, must be equal the total kinetic energy at the bottom of the inclined plane 1/2 mv squared plus 1/2 I omega squared. So this is the conservation of mechanical energy in a system. So we're going to use these two equations for this equation for solving the questions. For example, let's apply this. A solid ball with a mass of 4.1 kilogram and radius of 0.05 starts from rest, right here, at a height of 2 meters. So that is 2 meter height, and rolls down 30 degree slope. So this is 30 degree slope. What is the translation speed of the ball when it leaves the incline? So we will find this. Okay, mechanical energy at the top is potential energy. Potential energy is equal to mass times h times mgh. Mechanical energy at the bottom is what? Kinetic energy, total kinetic energy, 1/2 mv squared plus 1/2 I omega squared. So you will calculate them one by one. You are going to make them equal because according to the application of the conservation of kinetic energy, so these two numbers must be equal. mgh, let's find it, potential energy. M, how much? It is 4.1 times g, 9.81. H is how much? 2. So when you multiply them, you will find the mechanical energy, total mechanical energy at the top. 4.1 times 9.81 times 2, which is equal to 80.44 joule. This is the total mechanical energy at the top. So it must equal the total mechanical energy at the bottom. So kinetic energy is there at the bottom. It's total mechanical energy. So instead of this, I'm going to write 80.44. So 80.44 is equal to 1 over 2m. M is how much? 4.1 times v. We will find v squared plus 1 over 2i. Yes, I is needed. It's a sphere. I for sphere is 2 over 5 mr squared. So I'm going to write here 2 over 5 mr squared times omega squared. Omega is what? Omega is equal to v over r. I'm going to write omega squared v squared over r squared. V squared over r squared. Why did I do that? Because they will simplify. I don't need to write r in this equation. So this equation becomes this way. 1 over 2, it becomes 2.05. V squared plus 2 will simplify. 1 over 5 v squared. 1 over 5 is 0.2 v squared. Then 80.44 is 0.2 plus 2.05, 2.25 v squared. So 2.25 divide 2.25. So it becomes, they simplify. 80.44 divided by 2.25, it becomes, so v squared becomes 35.75. Now let's get the square root of this number. It becomes v is equal to almost 6 meter per second. If we didn't make a mistake, calculation mistake, this is the answer. However, in such a question, there's a shortcut. That shortcut is this. If an object is released from top of rigid object, it can be a cylinder, sphere, or spherical shell from this point, you can find its translations at the bottom by this equation, 2gh, the root of 2gh over c plus 1. What is c? C is the coefficient of moment inertia. For example, sphere. For sphere, it is 2 over 5 mr squared. So this is c here is 2 over 5. For cylinder, 1 over 2 mr squared. C is equal to 1 over 2. So you are going to write c here. H is the height of the object. G is the gravitational acceleration. You can find easily the translations